Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Huzaifa Bajwa and I am from the Department of BS Chemistry and my ID is 007. Today I am going to present topic about a Nobel celebrity who got Nobel Prize for his great research in the field of chemistry, and his name was Aziz Sancar. He is an Turkish American biochemist. He got the Nobel Prize in 2015 for the research on mechanistic studies of DNA repair. Sancar received the Nobel Prize for chemistry, shared with Swedish biochemist Thomas Lindell and American biochemist Paul Modrich. Mm, the earlier history of Aziz Sancar is he was born in a lower middle class family on September 1946 in Avali Sever, the province, Mardin, Turkey. The seventh of eight children with two half brothers. His father Abdul Ghani was a farmer, and his mother Mariam Sankar took care of the children and the house. He spent his early childhood in vegetable garden with farm animals, which were the source of their house income and nourishment of their family. Moving toward the educational history of Aziz Sancar, he was the top student in his class throughout his primary education in Sever and his secondary education in Modern. In 10th grade, an excellent chemistry teacher inspired him to become a chemist. Sankar joined Istanbul Medical School in November 1963 and received an MD in 1969 and subsequently worked as a local physician near Sever. In 1973, he went to the United States to study molecular biology at the University of Texas, Dallas, receiving a master's degree in 1975 and a PhD in 1977. Uh, Dr. Claude Stan Robert was his mentor at the University of Dallas. He then accepted a position as a research associate at Yale University and in 1982 joined the faculty at the University of North Carolina School of Medicine, where he later served as a professor of biochemistry and biophysics. Now, coming towards the research project of Sankar. Sankar's research has focused on how DNA can repair itself after a damage. He discovered enzymes which can recognize mutations caused by ultraviolet radiation and then cut the DNA to remove the damaged genetic code. The oxygen repair that the Sankar synthesized is known as UV or AB nuclease, oxygen nuclease or Xe nuclease. The enzyme specifically target this enzyme specifically target DNA that had been damaged by ultraviolet or chemical exposure, cutting the affected DNA strand at each end of the damaged region and thereby enabling the removal of damaged nucleotide, as shown in the diagram here. The ultraviolet light causes the thiamine dimer formation, uh, which which is uh, replaced by the thiamine in single bond by a UV or nuclease enzyme. Mechanism of nucleotide oxygen repair. Following steps are involved in nucleotide oxygen repair. Number one, damage. Number two, damage recognition. Number three, oxygen. And number four, oxygen repair. Nucleotide oxygen repair. Damage. The first point of nucleotide oxygen repair is damage. The ultraviolet wavelengths in sunlight damage DNA by converting two adjacent thiamines into a thiamine dimer, which is potentially mutagenic, carcinogenic, carcinogenic, or lethal to organism, causing mutations in the genetic sequence. As the diagram shows, the ultraviolet light causes the two thiamine to form a thymine dimer. The next step is damage recognition. Damage is recognized in humans by cooperative interactions of RPA, XPA, and XPC proteins, and in E. coli by the UVRA enzyme. Excision. The next step is excision. Excision of the damaged nucleotide. TFIIH contains the XPB and XPD helicases that unwind the helix and recruit the XPG and XPF nucleases to make the 3' and 5' incisions on the damaged strand from both sides. The dual incision. The human excision repair system incises the damaged strand 20 to 22 nucleotides from the 5' end and 5 nucleotides from the 3' end to the damage to release an excised oligomer of 20 to 30 uh, in length. Now the next step is repairing. The gap produced by the excision is filled and ligated by DNA polymerase and ligase by synthesizing a 30 nucleotide repair patch as shown in the figure. Here, the ultraviolet that causes the thymine dimer formation is excised by the TFIIH recruitment by the helicases. This we can see that from the 5' region, from the 5' and that the enzyme incises 22 nucleotides from here, from this side, and 5 nucleotides from 3' end, and excite an oligomer of 30 mer. The resynthesis, the DNA ligase and the DNA polymerase resynthesize the patch removed by the TFIIH recruitment, and the damage is repaired. Overall mechanism of human nucleotide excision repair is shown in the figure. Let's have a look, brief look. This is nucleotide DNA strand. When ultraviolet light falls on the DNA strand, the two thymine forms a thymine dimer, which is recognized by XPC, XPR, RPA, XPA proteins and recruitment of TFIIH. The TFIIH contains XPA, XPC helicases that unwinds the DNA duplex, and the RPA enzymes, RPA proteins causes the excision of the damaged nucleotide. Here we can see that from the 5 in the 5' and 22 nucleotides, and from the 3' and 5 nucleotides, the collectively dual incision process, and the oligomer removed is of 30 mer oligomer, 30 oligomer. And that the gap produced by the excision of the damaged strand is filled by the DNA polymerase and ligases, and the damage caused by the ultraviolet is repaired in this. This is all from my side. Thanks.